So it is the repulsion between the d orbitals and the incoming electrons of the ligand which is responsible for the splitting of the d orbitals in the different field. Let us take a look, students. We have 5 d orbitals, that is dxy, dyz, dzx. We have dx square minus y square. D orbitals are there, and in the octahedral complex, if you consider, the ligands are like this. That means if you draw a coordination axis, can I draw the coordination axis like this? If it is x-axis, this will be y-axis and this will be z-axis. Clear? So this will be, for example, x-axis, this will be y and this will be z. For instance, consider this. That means they are at 90-degree angle, right? So that what does it indicate? It indicates that in the octahedral field, ligands are coming along the coordination axis. Ligands are coming along the coordination axis. But let us take a look at the d orbital. Don't you think that there are 2 kinds of d orbitals we have? One set is this, another set is this. Right? One set is dxy, dyz and dzx, another set is dx square minus y square and dz square orbital. Because if you consider the nature of this, dxy, dyz and dzx orbital, lobes of the d orbital will be present between the coordination axis. If you are having a d orbital like this, that is a double shaped one, right? This double shaped d orbital, whatever we are having in the case of dxy, dyz and dzx orbital, this lobes or the electron density what we speak will always be oriented between the coordination axis. If it is a dxy orbital, the electron density will be between x and y coordinate axis. That is, this is x, this is y. If it will be between x and y coordination axis. Right? If it is yz or dyz orbital, the electron density will be located between y and z coordination axis, and if it is z and dzx orbital, electron density will be between z and x coordinate axis. Try to make it clear. Whereas another kind of the d orbital we are having dx square minus y square and dz square orbital, where the electron density or lobes are focused. Electron density or the lobes are along the coordination axis, right? So electron density will be along the coordination axis as far as dx square minus y square and dz square orbital is considered. If you consider dx square minus y square, for example, this is x and this is y, how do you write the dx square and dx square minus y square orbital? This is the orbital where 2 lobes, both the lobes, if you consider x orbital as well as the y orbital lobes, will be focused along the coordination axis. That means electron density is there along the coordination axis. If you consider the dz square orbital, for example, if it is a z orbital, will be having a lobe along the z axis and again a collar-like lobe along the xy axis. Right? That is what is called as our dz square orbital. So that means, what I mean to say is, there are 2 kinds of orbitals you have. One is dxy, dyz, dzx comes under the one category where the electron density is between the coordination axis. If you are having the coordination axis like this, the electron density will be in between. Whereas one more kind of the d orbital you are having where the electron density is along the coordination axis. If you are having coordination axis like this, the electron density will also be along the coordination axis like this. It will be along the coordination axis, it will be along the coordination axis. On the other hand, if you are having dx square dxy orbital, this will be the lobe orientation. That means the electron density will be in between the coordination axis. So 2 kinds of the ligand, 2 kinds of the d orbital, 2 category of the d orbital. That is one category between the coordination axis, electron density, another category along the coordination axis. Try imagine this, students. In the case of the octahedral complex, ligands are coming along the coordination axis. Ligands are coming along the coordination axis and 2 of the d orbitals are along the coordination axis, whereas 3 of the d orbitals are in between the coordination axis. Don't you think that? Don't you think now that since the ligands are coming along the coordination axis, 2 of the d orbital whose electron density are along the coordination axis will be having a direct overlap? For example, if you consider this is a d orbital, this is our ligand. Ligands and the d orbitals are having a direct encounter. If the 2d orbital whose lobes are along the coordination axis will be directly encountering the ligand, that is, the repulsion will be very high. On the other hand, rest of the 3d orbital, ligands are coming along the coordination axis. The lobes are in between the coordination axis for the dxy, dyz and dzx orbital. Don't you think that these 3d orbitals are little away from the ligand field? These 3d orbitals are little away from the ligand field, or in other words, what I mean to say is, in the octahedral field, dx square minus y square and dz square orbital, whose lobes are along the coordination axis, will have a direct encountering from the ligand. That means the electron-electron repulsion, ligand-electron and the d electrons present on the dx square minus y square and dz square orbital will be having a high repulsion, or this energy will be raised. Whereas these 3 ligands will be having a lesser repulsion from the ligand field because they are away from the ligand field. Since they are away from the ligand field, what happens is the electron-electron repulsion will be decreased, or repulsion decreases means their energy will come down. Or in other words, can I say that in the octahedral complex, there is a splitting happens in such a manner that you have 5d orbitals. That is, if it is an hypothetical field where, for example, the ligand field is equally spaced, then we should have all the d orbitals which has to be at the degenerate state. That means which has to be at the same energy level. But it is not so in reality. In reality, 2 of the d orbital, dx square minus y square and dz square orbital, dx square minus y square and dz square orbital will have more repulsion compared to that of the dxy and dyz and dzx orbital. What's happening in reality is 2 of the d orbital will be having a energy raised. 3 of the d orbital will have a lowering of the energy. Right? This is the splitting pattern in the octahedral complex. In the octahedral complex, what is happening in reality is these 2d orbital will have higher repulsion from the ligand field. That is why this will have a rise in energy, dx square minus y square and dz square orbital. Whereas these 3 orbital will be having lowering of energy, dxy, dyz and dzx. That is, splitting happens. This is the hypothetical field we are having. From the hypothetical field, there is a rise in energy for the dx square minus y square and dz square orbital. dxy, dyz, dzx orbital will be having lowering of energy. One thing has to be kept in mind, these 2 orbitals combined together will be writing Eg orbital. G actually indicates the center of symmetry, students, which will not be there for the tetrahedral complex center of symmetry. So when we write these orbital for tetrahedral complex, you will observe I will write it as E and T2. This is what is these 3 orbitals combines together, we refer it as T2G orbital. Again, G indicates the center of symmetry because you can go any side, there is a center of symmetry in the octahedral complex, right? There is, you can cut into you can go this side, you will encounter the same species at the same distance, right? That is why you have a center of symmetry, right, for the octahedral complex. Whereas the tetrahedral complex doesn't have, that is the reason we will omit G. G will be omitted when we go for the tetrahedral complex, right? So one thing has to be kept in mind again. See, amount with which this will be law of conservation of energy comes into the picture. Amount with which the destabilization happens, same amount with which the stabilization happens. That is, this amount will be, these 3 d orbitals will be decreased in energy, will be equal to these 2 orbitals will be increased in energy. That is what the law of conservation means. This is Eg orbital for you and this is T2g orbital for you, right? So this is how the splitting happens in the octahedral field. This is how the splitting happens in the octahedral field.